Welcome back, Physics 30. So we are going to continue on. We're going to do some examples of these wires and magnetic fields here. So let's look at this question here. It says, it actually says determine the magnitude and determine the direction of the magnetic force. It's good to know because they gave us a picture. We can actually do that. So we're going to assume, it's also useful to know that if you were to draw an arrow on this from the short side on this guy, so this is what the battery looked like originally. If you were to draw an arrow on this, the arrow points towards which direction the electrons are coming out of. So I know which way the electrons are going here. They're going this direction. And it's this kind of three-dimensional picture. We could just say that that's kind of going into the page at that point. So if I wanted to determine the direction that this wire is going to be forced here, I'd have to first of all determine which direction is the magnetic field. There's my magnetic field there. Okay. And then we're going to use our hand rule. So I'm going to put my thumb into the page. My fingers are going to go in the direction of the magnetic field from north to south. And if I look at that, if I look at that there, my force is upwards. So there's my magnetic force. Now remember that this is not going to create a circular motion like a free particle. It's just going to create an overall force upwards in this case. Of course, there's gravity pulling this thing down. There might be a question later on there. It says determine the current to make sure that this wire is levitating there to kind of counteract gravity. You have to know more information like the mass of the wire and stuff. Okay, so what do we want? We want to determine the magnetic force. I'll just change that to black here. We want to know the magnetic force, which is going to be, because we're talking about a wire, it's going to be ILB. And the L has to be perpendicular. It looks pretty perpendicular in this picture here. So we have all the information we need here. We got the I, and the I is in current, or is in amperes, sorry. That's our current. It's in regular amperes, so I don't have to change anything. Our B is not in regular Teslas, it's milliteslas. I'm going to change the milli into regular Teslas. Milli, I should say. And the length of the wire is also not in regular meters. It's in centimeters right now. So I'm going to change that into regular meters. So those are my numbers I'm going to use there. So I pull out my calculator. Punch them all together and I get a force here. So my magnetic force, using the numbers on that side over there, with 3 sig digs is 7.50 times 10 to the negative 4 newtons. And I know what direction it is. It's going upwards. So I can put those together and get my final answer. Okay. This is the question I was just talking about. I want to float this wire. So I'm thinking about a wire in a magnetic field. Let's just think of this as a cross section of my wire here. I'm going to want two forces on this to make sure it floats. Because gravity is going to go down, I have to make sure that the magnetic force upwards matches that gravity. So I'm just worried about the magnitudes here because I know the directions have to be opposite. So let's figure if we can find out some of these things, like what's the minimum current? So in this question, I'm looking for the I out of the formula ILB. Mass of gravity, sorry, force of gravity here is just mass times gravity. And I can just rearrange this equation to get I by itself. So it's mg divided by LB. Okay. We know most of the stuff here. So like our mass, 0.06 kilograms. Our length of our wire, it's 1/4 of a meter, or sorry, 3/4 of a meter. Our Teslas, or sorry, our magnetic field is in Teslas here. That's supposed to be a B. And gravity obviously is 9.81 newtons per kilogram. Okay, so we know all the numbers that we need. So I'm just going to punch in my calculator here. Divided by my wire length and divided by my Teslas. So to get this to work, to levitate or to float here, we're going to need a current of 5.23. I'm going to change that to 2 sig digs, because that's what the question says. So 5.2 amperes. That's capital A for amperes. Okay. Let's see what else we have here. Okay, so before I do this slide, because this slide is going to be helpful, it's going to talk about what happens when I have 2 wires that are side by side. They're not inside an external magnetic field, but they're 2 wires side by side. They have current flowing through them, or either way in the same direction or both opposite directions here. But when current is flowing through them, what happens to those wires? Because now they create 2 magnetic fields. Magnetic fields are going to interact and they're going to produce a force. So what I want you to do is I want you to watch the video that's going to be in the doobly-doo below or in the Google Classroom there that has this guy in it, this guy right there, that guy with the orange shirt. Once you watch that video, come back here. I'm also going to load up an applet that's on the bottom there. It says here MagLab. There's a couple more MagLab things I can show you about this. So come back when you finish watching that video. Okay, welcome back. So before I go back to that picture, before I go back to this picture here, I want to look at these 2 MagLab descriptions here. So this one here is the one I want to watch first of all. Okay, so this here is a set of wires. And if you remember, you watched the video. And when you watched the video, all the wires were moving in the same direction. All the current were going in the same direction. So we call that, they're all parallel to each other. So all the current would be going one way. So here, you see in this little picture here, I paused it. The current, they have conventional current, so you have to think about going the other direction. So the current would be actually flowing this way. Splits off here, so both the current and these wires are going in the same direction. When the current's going in the same direction, if you remember the video, it contracts, right? So they're going to contract inwards and pull each other in. Now the current was going opposite direction. So in the video that she talked about those 2 wires, one going towards the device and one going away from the device, they kind of pushed away from each other. So those guys are going series. So you could see in this picture that the current is going one way in the one wire and it's going the other way in the other wire. And it creates the 2 magnetic fields. And you can see the magnetic fields that's producing there. Right here, producing these 2 magnetic fields. And the 2 magnetic fields in this case kind of going in the same direction. They're going this way. In the previous one, they were kind of going opposite direction. So one's going this way and one's going this way. No, I can't do it mentally. Kind of like that. I guess going this way. Okay. Now, we'll figure it out when we do the picture over here. So let's figure out why does this happen? So why is it that if they're going in opposite directions, they repel, and when they're going in the same directions, they attract? So let's go back to the picture. And to do this, we have to think about those mini magnets we were talking about before, those invisible magnets. So what you're going to do is you're going to draw an invisible magnet here, right here. You're going to draw an invisible magnet right here. So here they got the wires where the current is flowing in the same direction, into the page, into the page. You can see they drew the circular magnetic fields based on the left-hand rule again. So into the page, into the page. Then my fingers are going to curl around this way. So you can see that they drew it that way as well. So into the page, going around this way. And in a counterclockwise motion. Okay. So when I do that and I draw these little mini magnets here, I'm looking at the magnetic field here. So it's coming out of the top. Remember, our rule is if it's coming out of the top, that's the north of this magnet, this invisible magnet that doesn't actually exist there. And this is going into the bottom, so this is south. On this side over here, it's coming out of the bottom, so that's the north. This is going into the top, so that's the south. So here's the north and the south beside each other. Here's the north and the south beside each other. So these 2 invisible magnets are going to attract each other, but they're attached to this magnetic field, which is caused by this wire. So this wire is going to get pulled this direction. So they're going to pinch in. So it's called the pinch effect. Okay? So there's going to be a magnetic force here, and there's going to be a magnetic force here. Now, if I were to draw those magnets again on this one here, you can notice I did the hand rule again. So that one's going to go counterclockwise, but the other one where it's coming out, it's going to go clockwise because it's coming out of the page, curls around clockwise. You can see that in this picture here, you can just go in that direction there. So if I were to draw the field here, so this is coming out of the top, so that's the north, out of the top, so that's the north, into the bottom, so those are both south. So I have a north versus a north and a south versus a south. They're going to repel each other because they're attached to these wires. Magnetic fields are created by the wires. The wires are going to push out from each other. So they expand outwards. So you can see that in this example here, that these are going in the same direction, so they pinch in. You can see the electrons flow in the same direction. Electrons flow in opposite directions, they push out from each other. There you go. Another useful, interesting fact is like this is what we call the Rogence contracting helix. It's the same idea what we just did. So I just going to create a little snippet here of this device. Now, what happens in this device here? So once I turn this on, or when this thing turns on here, this little battery is going to produce a current. It's going to flow through this device here. It's going to go around this little spiral all the way down, go into the mercury, and then, I have the wrong wire going in the wrong spot here, but it's going to go through the circuit and complete the circuit. So the mercury is just there so that this thing can dip in, and all metals are conductive. So it's going to dip in, the current's going to flow through it, and then it's going to do what it does. So you're going to see what's going to happen here when I turn this on is that, if I can just zoom out here, when I turn this on, now come on, turn it on. Oh, there we go. So when I turn it on, it does this little bounce, right? You can just see a little spark down here. I had a little sound effect before. There you go. Now it's bouncing up and down. Now, why is it bouncing up and down? It's the same rule as why current flowing in the same direction contracts inwards. So if I go back to that picture of this device here, so as this current is flowing through this one here, all the current on the outside edge out in the front here are all going in the same direction. So all of these wires will attract each other. So they'll attract each other, they'll pull upwards, and then the current's gone. So gravity will take over and pull back down. Current will flow through it and then pull it back up. And then it'll just keep on going up and down, up and down, up and down. So that's how that device works. There's a little pinch effect. Cool. All right, so in the next video, what we're going to talk about here is we're going to talk about the motor effect. How does it produce motion? So right now this is fine and dandy. It's really hard to maybe harness this motion into useful motion. So we're going to somehow create using magnetic fields, using electric fields or electric current. How do we produce useful kinetic energy from it? So we're going to talk about the motor effect and how do I create from kinetic energy useful electrical energy that I can transmit around as well. So we're going to talk about the motor effect and the electric or generator effect in the next video. I'll see you then.